Right, thank you all for being here. Today I'm going to talk about unusual organically preserved microfossils from the interglacial interval of the late Neoproterozoic, just before the rise of animals. And so this is a part of a large collaborative project with paleontologists and sedimentologists studying the Neoproterozoic to Cambrian Earth transition on the Grummond Peninsula up in the Norwegian Arctic Circle. And here I will present just one part of that work, deeper down in the stratigraphy. So multicellularity has evolved multiple times in Earth's history, independently in various groups. But complex multicellularity amongst eukaryotes is actually quite rare. There are now 6 clades that have it. There are animals, some red and brown algae, embryophytic land plants, and 2 groups of fungi. This schematic timeline this schematic timeline here shows major events in the evolution. In the Precambrian, with the time on the x-axis. So I'm trying to, there we go. With time on the x-axis. And we see that complex multicellularity has evolved quite early on, actually, about 1 billion years ago. But then it took some time until multicellular organisms grew big, and we see that with the appearance of the ediacaran biota. And so animals and plants, 2 most common, most popular multicellular organisms, are quite a recent affair. And examples of early complex multicellularity in the rock record are also quite rare. They're mostly also restricted to exceptional preservation. And appearance of first macroscopic visible life is marking the end of the Neoproterozoic era. And we see this event in the rock record with the appearance of the ediacara type biota, a fossil collectively termed the ediacara type biota. And these are complex, soft-bodied fossils, which probably include a mix of stem and crown group animals, and most have no living representatives. Increased complexity is also seen across kingdoms, as we see in these complex multicellular algae from Jauhe. And these fossils occur after several global low-latitude glaciations, commonly known as the snowball Earth, which is sometimes invoked as a catalyst for the evolution of complex life. But if we look at the timing in more detail, here on the y-axis, and then we see the stratigraphic ranges of the ediacara biota, we see that there was actually a huge chunk of time before the end of the snowball Earth and then the appearance of the ediacarans. And then during this time, we're mainly dealing with microscopic forms. So what happens to eukaryotes after the snowball, before the life got big? What innovations are there among microscopic multicellular forms? So to understand how life fares in the aftermath of the Cryogenian and through the Ediacaran Ice Age episode, the guest years, I went to a place which contains a continuous succession of late Neoproterozoic glacial, non-glacial, glacial units, and that is the Grummond Peninsula. It is located just off of Norway's northernmost tip on the mainland in Finnmark. And it has widely distributed Neoproterozoic units, including the glacial strata. And this is a pretty busy geologic map of Grummond, but the point here is that it contains almost continuous a succession from the Cryogenian to the Ordovician here at the tip. And so, as always, as is the case usually with the Arctic, the exposure is excellent, so this makes it a really good place to work. And we worked mainly on the southeastern shore. On the left is a schematic stratigraphy of the studied Neoproterozoic to Cambrian strata on Grummond. Our initial goal was to use biostrat to provide a better temporal framework for these units, especially these glacial strata, the diamictites, Morten's Ness, and Smallfjorden here. And these were traditionally correlated with the Marinon and Gaskier's glaciations, respectively, but there were no firm geochronological data. And so just to put things into context a little bit, here we have the Vestutana group, which is mostly composed of siliciclastics, and It includes the Precambrian-Cambrian boundary up here that is seen in the appearance of a trace fossil Tropichnus pedum in the uppermost Stepogate formation. A bit below, we see the diacaran biota. They occur for a couple of 100 meters through the Indre Elva member, also in the Stepogate formation. And these include the holdfast discoidal taxa, like Hemilura, Aspidella, as well as multivein forms. And then below, at the base of the Indre Elva member, we have these Protistan impressions, Paleopachycnus. But let's take a step even further down the stratigraphy to time before visible life. And so the Nyborg formation is composed of about 300 meters of shales and siltstones, purple shales and sandstones in the middle, and then sort of more muddier shales towards the top, where we have the most abundant microfossils. The overlying Gaskier's equivalent, Morton's Ness formation, is a massive dimictite. It's bedded in places, but it also contains a fine-grained matrix, and we can look for microfossils there. The Nyborg assemblage of the interglacial interval contains moderately preserved large organic wall microfossils, including some diagnostic Doshanto-Bertatica acrotarchs, which then corroborates the diacaran age of this formation. And these taxa are common on lower diacaran strata on Siberian and Eastern European platforms. In contrast, the Morton's Ness assemblage, the glacial one, is more depauperate and contains mainly bacterial fossils and almost no eukaryotes. But what was especially interesting to me were these abundant, odd carbonaceous fragments that we saw. Like acrotarchs, these were extracted from the shale matrix via palaeontological maceration in hydrofluoric acid, and larger fragments were picked with a pipette. And we also have them in situ, as seen in this thin section. Scanning electron microscopy revealed quite complex structures of many stacked and occasionally intertwined tubes, which can be either closed or often terminate in sort of cup-shaped openings. And sometimes these openings have kind of an inner regular round opening that then extends into the tube itself. And we named this oddball Seatinema, meaning cup thread, for the feature of tubes terminating in cups. And the cups also have a small, regular inner opening. They're also present in thin sections, so we can exclude, they're kind of unlikely to be contaminants. And all of the specimens that we saw in thin sections and in macerates are truncated and show signs of transport, like clasts. So perhaps they were a part of a larger structure. However, no other morphologies, like different organ taxa, were covered in the Nyborg formation. So the tubes and cups may represent kind of a most resilient part of this perhaps larger organism that maybe had a higher preservation potential than the rest. And so I went on to measure a lot of specimens and their elements. And it turns out that the ones in thin section are larger than the extracted ones. And this could be, of course, due to processing, although we did use the low manipulation method. As seen on the right, the cup diameter and tube width are pretty uniform on a given specimen, and they don't really differ across specimen. Each box and whisker represents a full specimen that was measured, and all the measurements in that specimen. Like many organic walled microfossils, Seatinema is also preserved as organic matter. Chemical characterization via EDX has shown that the fossils are composed predominantly of carbon. The second most common element was titanium, but I think that comes mainly from abundant titanium oxides in the Nyborg formation, and then they get glued onto the specimen as a residue. Raman spectroscopy confirmed this carbonaceous composition. These peaks correspond to disordered and graphitic bands of organic carbon, which are associated with carbonaceous matter that has undergone moderate thermal alteration, as we'd expect from this unit. So the fossil was organic walled. It had characteristic tube and cup arrangement. Transport probably led to its fragmentation. And so its original size is quite unclear. This is how we sort of reconstruct what we have, but it was probably a part of something bigger. Setinema is potentially stratified, since in best preserved specimen, these cups only occur in one end of the fossil. So what do these things represent? Well, we can compare our fossils to clades that have evolved complex multicellularity over time, such as tissues of algae, fungi, and animals, or some colonial protists, perhaps. And so in light microscopy, Setinema resembles sheets of a multicellular eukaryote from Paleoproterozoic of China that was described a couple of years ago, interpreted as a fragment of something larger, such as these co-occurring carbonaceous films. But those fossils lack tubular treads, so we can exclude those. Colonial protists share some general similarities with Setinema. Some slime molds, such as Metatrichia, can produce tubes that end in these domal structures that sometimes that can open up when they reproduce. And coniflagellates produce tubular theca. However, these are superficial, and while we'd expect these groups to have evolved by the Ediacaran, they have a low preservation potential. The Neoproterozoic fossils are also similar to a putative Ediacaran sponge, Eocyatospongia, described from the Doshantou Formation in China. It is much larger, though, but its walls contain this sort of reticulate structure. And these have been interpreted as demosponge papillae or choanocytes. So tentatively, our fossil may represent wall fragments of this larger fossil, whatever it is. Its sponge affinity was recently questioned because its size would preclude efficient filter feeding that's needed by the porifera. However, there are further similarities with extant demosponges. More precisely, their larvae, which have a differentiated cells and tube and cup morphology as their epithelium, external layer. Now, sponges are not unexpected at this time. There are sponge-specific biomarkers from mid-Neoproterozoic onwards. A new one was reported just a few months ago. But it should be noted that there are no unambiguous fossil record of Precambrian sponges. So we're not sure if they don't biomineralize, if they would ever get preserved in the rock record. Even more, though, there are similarities with an enigmatic group of Paleozoic fossils, nematophytes. These are usually charcoalified organic remains of exceptional preservation. And they're polyphyletic, they represent different things, fungi, algae, some problematica as well. And so regardless of what they are, Setinema is kind of the oldest organism with this type of organization. Most characters are shared with red algae, though. And this group also has representatives in coeval units, such as the Doshantou Formation in China, in phosphorites in the exceptional preservation, like this Mangania. And they have a comparable external layer to modern red algae like corallines and floridophytes, and the authors compare these with these species. But also there are many other red algae that produce similar structure, the epithelial layer, like this one. Himantalia actually sheds its epithelium throughout life as an overgrowth prevention strategy. And so it can stop bivalves from settling onto the alga and then sort of munching it to death. And so to sum up, our Neoproterozoic fossils are similar to a lot of different things because lots of things out there produce this tube and cup morphology in their external layers. Red algae, demosponges, potential fungi. But there seems to be kind of a common thread between these things. Most of these analogs have an epithelial layer, external layer, and those would have benefited the organism in avoiding overgrowth, epithelial sloughing, limiting fouling, reproduction, or even water filtration. So even though we're not sure exactly what this was, we can guess its function from these analogous similar organisms. And so just to sum up, we have this unusual organical microfossil from the interglacial interval of the earliest Ediacaran. We're unclear what it is. It's similar to a lot of different unrelated clades, but they all have one thing in common, which is an epithelial layer. So we're assuming that these fossils represent an epithelium of some sort. And this is one of the earliest records of complex multicellularity that's not preserved as a part of a conservat Lagerstätte, so outside of the windows of complex preservation. And with that, I would like to thank Diggermullen Early Life Research Group, and especially Annette Högström, who organized expeditions to far Diggermullen, my colleagues at UCSB, and everybody who gave us money. Thank you.